Hello, my friends. This is Dr. Mohamed Nezami again with another video on the RF and microwave device design and modeling. Although I did a lot of these modelings in HFSS, ANSYS HFSS, but the very same concepts are applicable to all of the other packages as well, like CST and Mycian and WASP.NET and the other few other ones that I can't recall right now. But any of these, anyway, I'm an independent contractor for RF and microwave devices. I design passive and active circuits anywhere from DC to 32 gigahertz. If you have any need for to offload your on-site engineers with some of the design issues, or an existing design that has an issue with performance, or you need validation of some existing design, please contact me at the phones here or the email, and I'll be glad to help you. My rate is very reasonable. And I have a very rapid way of developing prototypes. Okay, so anyway, please share this video and hit the like button if you could. Also, you could review my other lectures. We have covered almost 10 videos right now on various designs, from microwave to coplanar, to planar circuits, the transitions. We've covered the OMTs and polarizers designs. We've covered surface integrated waveguides and filters. And so today we're covering waveguide filters. Okay, I know this is there is plenty of work. It's very mature. Design approaches are in existence. So today, hopefully, this video will help some of you on understanding the design concepts and the modeling tools. So, like I said, we are going to talk about waveguide filter designs and 3D modeling today of those filters. Waveguide filters, they have variety of uses. We could, at any time you inspect any antenna feed system, you will very much stumble onto waveguide filters. Now, these filters can be anywhere from transmit rejection filter on the LMB branch of the OMT, like in this case, for instance. You see here, there is a band pass or band reject filter in here, which basically rejects the transmitted signal leakage from this path. It rejects it so that it doesn't leak into the LMB. Or we could see them on large aperture feeds, like in this case, and you can spot filters in a lot of areas between the feed horn and the buck and the LMB. Like in this case, this feed system in here, you could see the waveguide filters. All of these with these tunable screws are filters, as you can see in here in the front. Same thing in here. This is a Diplexer, so as same as this one too. This combines two channels. Okay, so you basically can see here is a filter and here is a filter, and this is a common port. So this either can be diplexing or multiplexing. So same as what's done in here. So waveguide filter designs are basically like all other filter designs, same approach, except when it comes to the implementation, we implement the components, the susceptances, using irises and stops and posts, basically. So basically, we could start out with a filter that we design and synthesize and even optimize the frequency shape using lumped elements. And then we can compute from those the K inverters, and the K inverters are then replaced by shunt inductive loads. These are irises or susceptances, and then we space them basically we put on the back and the front, we put between the two susceptances, we place a waveguide cavity or a half wavelength. Okay. The structure then is modeled. Usually the design equations will give you the initial dimensions, and then you can always put the structure in a 3D EM and then run optimization to get the final dimensions of the filter. And then, of course, from there, you have to create a mechanical drawing for the CNC machining or 3D printing, whatever method happens to be that you chose to fabricate the filter. Now, let's talk about the waveguide irises. These are the components that would mimic the susceptances that you see in regular passive lumped elements, you know. So for instance, in here, if you need to implement an inductor, so what we do is we narrow the x-axis aperture of the waveguide, either symmetrically or asymmetrically. This actually here is equivalent to an inductive plus Jx. A capacitive component, capacitive susceptances, that's if you reduce the height of the waveguide, either symmetrically or asymmetrically. Okay, now you might ask, what is the difference between these? They're exactly the same, except what happens in one case, if you're machining this has symmetry right in the middle, and this has symmetry right in here. So when you fabricate this in the CNC machine, all you need to do is cut this in half and fabricate one side and then duplicate it and then glue them together using screws together. Same way in here too. So now, if you need a trap, a resonator, an LC type response, then you basically have a metallic, metallic piece, rectangular metal sheet that reduces both the height and the width. And that way you implement basically this one and this one. Okay, and that's what happens in here. And of course, how do you support this inside a waveguide? Well, you put it into, you frame it with some material that has a very low dielectric coefficient, almost like foam or whatever. So if you need a series one, you basically implement a sheet that is basically done in this way. So you basically have the okay. And then we can get to the iris hole. Now, regardless of the shape of the hole in here, this will always have an inductive susceptance to it. So, okay, so let's see what there are plenty of different topologies of filters, but the most common ones that you will see people using is basically this one here, okay? Because it's very simple to fabricate, and the design equations, the equivalent of the inductance in here is very straightforward. And that's what you see in here. Of course, you could go either symmetrical or asymmetrical. Now, they're exactly the same equivalent. Same when you do an iris hole, same thing, but you don't see this very often. You always see these two. And now this one here, a lot of times you see it also implemented by cutting an existing waveguide. You just basically cut through it and insert sheets and solder them inside, okay? So you don't need CNCing on this one. You just get a standard waveguide and just make a slot for these metal posts and insert them in and enclose the slit where you put them in. Where this one here, you fabricate it with CNCing by getting either two pieces. This is symmetrical either in the middle here or in the middle on the sideways. And you basically put these together, okay? So all these type irises, they are placed at a half wavelength. The spacing between them at the center frequency of the filter. Oh, so this is a picture of two of these filters that I could find from the open literature. Here is one where they didn't fabricate it with a symmetrical axis, but what they did is they fabricated the inside and then they made a lid to this one, okay? And that's what you see in here. Now, I know when we draw them with a 90 degree 90 degree right at the irises, but this really here, this is very hard to do. Well, it's impossible to do with a drilling CNCing. So you always end up with a round corner type, and that's one of the things. So we start out, we could design it this way, and then we come in and we do fillets to fill these 90 degree in here, and we verify the performance so that we don't lose. And usually up to K-band, you don't see any issues with this. And I will show you today one of these examples where we take one design and after we verify it, we fill these so that it is very similar to this here. And we will see that the performance is not changed a lot. Now, this filter in here, as you can see here, now this is an existing waveguide. And so all they do is they made the slits and inserted the posts of the irises, and that can happen. Anyway, so my videos, in this video, you know, I'm not going to talk about how you synthesize these filters. I'm assuming that you have already gone through this situation where you either have a filter wizard designer that you enter in the center frequency, the bandwidth, the rejection requirements, the insertion loss requirements, the return loss, input and output, the group delay, whatever, and then you basically come up with the dimensions of the waveguide filter parameters, which are in this case are the iris dimensions and the both dimension of the iris itself, the length, and then the placement, the distance between them, which are shown in this case. For instance, in here we have the iris width, and which can basically we get the iris length in here, okay, from the width, because that's just b minus this divided by 2, because there's 2 of them, and the length between these two here. Okay, these lengths, as you can see here, they're not equal. We can start out with them being equal at a half wavelength, and then we could tune further than that. So we start out with it. Usually, the theory behind the filter synthesis, we start out with a bandpass filter. This is usually, even before that, we start out actually with a low pass filter. And then we transform the low pass to bandpass filter with, this is very, you could do it in MATLAB. There's a lot of tools online, and in MATLAB, there is an existing tool. So you can send, which is filter synthesis tools. And those are existent, do exist. So we're going to start past that. But anyway, you start out with a bandpass filter, and then you have a bunch of parallel susceptances and series susceptances, and you transform those with an inverter here representing the shunt susceptance and the series susceptance in here. And then you build this up, and then you transform from these the susceptances of the series part and the inverters in here, and you can come up with basically the dimensions of the irises, and that would be your waveguide. And then you construct it into the the 3D EM tool, and then run optimization and verification. Okay, so I grabbed this from several sources on the waveguide theory of irises. Whether you have an asymmetrical where you have the iris metal on one side, or whether you have symmetrical where you have the metals, the two metal on both sides. These susceptance basically is giving here as a function, and when you look at it, this is a function of the propagation constant, the a dimension in here, which is the width of the waveguide, and then the distance in here, the opening distance. Okay, so we have an equation like this, and that's useful. Then the other contrary to this, if you have symmetrical, it's very similar. Okay, so these two equations, a lot of people program in MATLAB, and then they compute the. So the filter synthesis is starting out like this. Okay, again, we have a half wavelength cavity in here, and on each side we have an impedance inverter. Okay, and from those now you can come in and define the inverters. They're really defined as a function of the filter coefficients first. These are the polynomial coefficients that you get usually from the table of the Chebyshev or Bessel or whatever table they have for the topology of the filter. For instance, you have the order of the filter, and then you come here and grab these G's, which are the coefficients, and you can plug them into these and compute the inverters, okay? And then, of course, transform that into irises, okay? Now, although we talk about filters, but in waveguides, but a lot of times what we have, the reason we design a filter is because we're designing a diplexer, for instance, in this case, like this here. Now, this diplexer in here, there's, for instance, you could have a receiver in here, a receiver in here, and then you need to combine them with a filtering in between. Or you could have a transmit and receive also. Okay, so we have a filter in here, a filter in here, and all we do, since this is 50 ohm, this is 50 ohm, this is 50 ohm, this is 50 ohm, you design this separate, or in this case, these here, and then you basically design a T junction, T waveguide junction, 50 ohm in, 50 ohm out, and here, and then glue it all together to make up a diplexer, just like you have in this case in here, for instance. We have a filter in here, we have a filter in here, and then we design a T junction with a wedge, of course. The design of this is standard. The equations and dimensions for this, you can look them up. There's a lot of places that have implemented this. So we go to the design tool in here, and then we start out with a blank waveguide, okay? And the blank waveguide, we come in, we put the dimensions, okay, and then we run it and just make sure that the filter that we're going to operate is somewhere the response is not in an overlapping area of the dominant mode with the next higher order mode, in this case TE10 and TE20 for rectangular waveguide. So for instance, in this case, if I'm designing a filter somewhere between, say, 8 gigahertz to the 14 gigahertz, then this would be appropriate, okay? I can't use this waveguide to design a filter between, say, 14 and 17 gigahertz, because I know that you could get the second room, the TE2010 will get excited in there and cause dispersion. Okay, so basically you run this, and then once you're verifying this, and then you can go and actually get the filter. And in this case, okay, so this is the filter, and the filter in here, we start out the way we design this basically is we get the waveguide. We use a little section of the waveguide as an input to establish the dimensions. And then we start with one, and then we copy it on one row, okay? And then we duplicate the whole thing on the other side. So it's pretty simple. And then so you end up with all of these design. And in this case, this waveguide filter, let's just look at the dimensions of the waveguide. This was the A and B's are 19 and 9, and that you can see that that's WR75 for the KU band. Okay, so we have all the dimensions in here are parameterized, and then we run it, of course, and then optimize. And in this case, for this filter instance in here, this is what you get basically. Okay, so we can see that this filter performs really well. It was designed between 11.75 to 12.5 gigahertz. Okay, so pretty good, nice filter. We could look at the E field and just see that in here, hopefully. Okay, this looks like it's a cutoff, it's a frequency below the cutoff, so it's not propagating. So let's check what frequency is that. So that's 16, so let's do 12. Since we have that solved, and there we go. So we can animate that, and 12, of course, is in the within the band. Okay, so we can animate that just to see how this thing is going. And there you go. So you can see that the signal propagates, and you can see how it's resonating between the two irises. Okay. All right, so, well, once we're done with that, basically we have a filter. Now you have to hand this over to a mechanical engineer or a machinist to make it, to fabricate it. So one way to do it is that you make the machinist make this here with an open, with the lid, with the top side is all open, making all of these here, CNCing all of this. And then you put a lid on it, okay, tie it really well with good tolerances, and then you get a frequency response. But with the only issue with this is you got, of course, the 90-degree in here. So let me look. Let's have a view on top. Okay, so if you look at, and of course, look at the lengths of these, that's as a result of the polynomial and the optimization. You can see the thing on them, and hopefully you maintain the symmetry so that this here is exactly the same as width as that, same length, so that if you decided to fabricate this with slice it at this axis with a symmetry both on this side and this side. If you look in here, this one in here, of course, when you have the CNC machine drilling all of this, this is a 90-degree. We can't do that. So we go ahead, and what we do is we create another filter where same filter, except we come in, and as you can see, we made these rounds in here. And so these, what you want to do is you want to consult with a mechanical engineer or the machinist, see that he can get you these. And once you do that, you can run it again and see that the response hasn't deviated a whole lot, okay? And of course, we can run this and animate it and see that it is in fact running smoothly with no issues. Okay, so you can see that and the key to this, of course, is you can see that the E field anyway doesn't really get close to the oops. Oh my goodness. I'm running the wrong one. Okay, let's look at this one in here. Okay, I apologize. Always get into this issue between when I get the multiple projects open. So let's look at this. And so if you look in here, you can see that the E field doesn't even get close to this because of the propagation, the ejection from the iris. It doesn't really get close to these edges at this mode. Maybe other modes it might, higher order modes. So let's animate this, and there you go. So you can see the E field is not getting anywhere close to these round edges. So that's why the frequency response in this case really didn't change a whole lot. Okay. So this was hopefully a good little introduction to waveguide filters. I'm gonna continue basically with the videos, going next to another topic which I will choose. So I will post these, and you can always please share them, and you can basically so just as a review, these bandpass filters, or we could do there are other filter topologies as well that we can do, high pass or low pass, and I didn't go through those, but those really, a lot of times what we do is we just we synthesize these filters as a step. So you can come into the as a step in the width of the filter to manipulate the cutoff frequency. And just to show you the idea, those filters in high pass and low pass are pretty simple to design a lot of times, and they're not really even designed. Just basically, so if you need a high pass filter, you just basically you create the dimensions of the waveguide so that will reject the low frequency. So you could move the A dimension of the waveguide. You can change it so that you can start at the frequency in here, reject these. If you have a low pass, you always do it the other way around. Okay, so basically you come in from small to wider, or and so forth. So you can always play with these. So if you have this here, and then another waveguide transition, another step in the width of the waveguide, so you or a decrease. If you have another width, it comes in here. So you can. So that's another way of really looking at the designing waveguide filters without using irises at all. Just basically. So in that case, for instance, you could come in to the waveguide and then have a step in the dimensions of the waveguide. And of course, now what happens is if this waveguide in here has a response that is like this one in here has a response that is below that frequency, that might be here, for instance. And you can play this trick again and again. Okay, so you can go this way instead. And so you end up with this cutoff frequency in here, and this cutoff frequency is way out here, for instance. So this will end up with an overall response that is like this, and so forth. So there's always a lot of these that you can play around with and do your manipulations. And hopefully this video was interesting to you. I welcome you to contact me regarding any issues. And again, this is Dr. Mohamed Nezami. I thank you very much for this video. Enjoy it, and we'll see you in the next video.